Okay. Was that the last time over there? Oh, I think last one we also discussed on how to solve the boundary layer. If you already know that uh, it exists. So several approach that has been used to solve the boundary. What is solve boundary means like you obtain the velocity distribution. Um, Solving means you want to get what is your velocity as a function of position from the leading edge. So if you have this, then you're able to get the velocity distributions, and then you're able to get your shear stress. And then if you're able to get the shear stress, then you'll be able to get your drag. So that solving means you want to get what's the velocity distribution, what's the shear stress, and then what's the drag, the friction drag caused by this shear stress. And the earliest one introduced by Blasius, so that's called the Blasius solution. He's a student of Randall, where he solves a laminar boundary layer for a flow over a flat plate without a pressure gradient. What is that mean without pressure gradient? Remember that on the there are forces, component of forces related to the pressures and to the frictions. So in this case, you consider there is no pressure gradient. So you're only going to have the friction component of it. And then the other approach is the momentum integral equations. So this to get the solution for laminar or turbulent boundary layers with or without a pressure gradient. But this is an approximate solution. Okay, let's go first with the Blasius solution for the boundary layer concept. We start with the assumptions that so it's really thin, so the velocity component normal to the plate is neglected. So what this means, like the velocity is only on one direction. So if this is the flow, each of the particle actually has this component of velocity u and also v. But this is ignored. Only u component is considered, and also u will change as it's increased. So if you can imagine the profile something like this. So in the boundary layer, you have different velocity. So you're going to have du over dy much greater than du over dx. So the change is only on the y directions because this is y direction. Okay, it's also zero pressure gradient as we noted before, and within the boundary layer, the viscous force is comparable to the inertial force. Means like we're going to account for the viscous force. So the Blasius start by introducing this velocity profile. U over free stream velocity is a function of, this is we call it eta. Eta is a function that we don't know yet actually, but we going to use that to find what the velocity profile is. Eta is y over delta. So if you have this boundary layer developing from the edge like this, so this is y directions, and the thickness at every x is the delta, right? So y over delta is your eta functions, and delta, the boundary layer thickness, is square root of viscosity times the distance x from the leading edge divided by the free stream velocity. Delta is proportional to the square root of x and inversely proportional to the square root of u. So this is the boundary layer thickness. Okay, there are partial derivations, and then there are calculus to be involved to solve the equations over here. But let me go ahead directly to the results on this one. So if you implement the analytical solution, there will be complex or non-even given the boundary conditions and then also the solution. So what Blasius did actually to obtain numerical solution of this differential equation, he used the power series expansion to solve this differential equations, and then the solutions is presented on this table. So there are so this is a pair. If you have the eta functions y over delta, so this is eta functions. This is same. Is actually this table consists of eta and then f accent eta. This one also here, or y over delta we defined previously. So you're going to have a list of eta, y over delta, and the f accent eta will be on the right column over here. So is this the solutions? Well, from this table, you're able to get this, the velocity distributions as a function of y over here. So you do have u equal to ux over here. You have velocity profile on the boundary layer, inside the boundary layer. So this is the solution that is provided by Blasius, and then it is summarized in terms of the parameter of the boundary layer. So Blasius solution consists of this underlying equation of the velocity profile, and then this underlying equation for the boundary layer thickness. And then if we take a look on the table, the previous table, we see that when eta is equal to 5 here, it is corresponding to the 0.9916 of u over capital U over here. It's equal to 0. Let's say 99 over here, which is equal, then that means this is where you have delta, because delta or the boundary layer thickness occur when u is equal to 0.99 free stream velocity. At this particular value, you have the boundary layer thickness. Okay, so what's the boundary layer thickness then? If you already know, if you have this solution, then you can find what's the y value accordingly. When this is 5, so when eta is equal to 5, then you have y equal to delta. So the distance from the wall is equal to the boundary layer thickness. Or we can modify this. So 5 equal to this. Y into delta, because now that's the boundary layer thickness. So delta, boundary layer thickness according to the Blasius solution, is equal to this, 5 times square root of viscosity times x divided by the free stream velocity, or rearranging into this. So this is the solution of the boundary layer according to Blasius. And then we can always derive other parameter accordingly. The boundary layer displacement thickness and boundary layer momentum thickness. We're able to do that also. So Blasius solution provide you a solution for the boundary layer velocity profile and other parameters. And then it fits nicely with the experiments. Although you have to be note that it applies only for laminar boundary layer conditions and over a flat plate, because you're going to have a different, if you have a cylinder or sphere, then you're going to have a different solution. For Blasius, although a very simplified solution actually give you a fundamental proof or verification of the presence of the boundary layer. So that's why it has a specific place on the discussions. Okay. Any question until this point?
No, sir.
Okay.
No, sir.
Yeah.
Maybe until example problem dulu ya, Pak.
Oh, we did this. We haven't discussed this one, right? Or we did last time?
Belum, baru kayak setengah gitu.
So yeah, so the takeout point on this is you understand the Blasius solution for the boundary layer thickness in terms of the delta and also the velocity profile and other parameters on this one. And of course, as I mentioned earlier, it has to be able to solve also for the shear stress. So for the Blasius solutions, the shear stress at the wall is this. How do we get this? This is actually from the solution that exists over here. TW equal to this. And if we put the Blasius solutions on the graph over here, so this is actually the table value, U over U capital, and this is the eta functions on the table. So the velocity profile is, and just over here you just plot until eta equal to 5, which is where you have the boundary. So you implement this inside the boundary layer until delta point over there. And then if you have different value of velocity compared to the maximum velocity, then you will have this different y value, different thickness. And means if you have a bit, higher velocity, then you have a different the boundary layer thickness. Okay, so that is the Blasius solution. I think we're going to have a example of this. Okay, let's yeah, so this is an example. So if you have water flows past a flat plate when an upstream velocity is known over here, and then we are required to find what's the velocity at the 10 millimeters from the plate. at distance of x equal to 1.5 meter from the leading edge? Well, we should assume that it is still inside the boundary layer, because otherwise we won't be able to use the Blasio solution because it applies on the boundary layer. So, before that, we have also to determine whether it's laminar flow, because Blasio solution applies only for laminar flow. So we calculate the Reynolds number for this flow. This is the velocity, presumed velocity. This is the x, distance from the leading edge, and divided by the viscosity of the water. We obtain 2.68 times 10 to the power of 5. For external flow, the critical Reynolds number is 5 times 10 to the. So this is critical Reynolds number. So it's still considered laminar. So we are justified to use the Blasio solution for this problem. So the Blasio solution for the velocity, Fx and eta is equal to u over capital U, and we want to know what's the velocity at 10 millimeters. So what's the velocity at y equal to 10 millimeters? So we determine eta is equal to y over delta, and then we know y 10 millimeters. So this is y value, and we can find delta according to Blasio's square root of Vx over u. So eta according to this flow is 1.091. So we go to the
Interpolation.
yeah. Yes, you have to use interpolation because this is 1.1, for example, but it's somewhere over here. Somewhere over here, then we have to find what's the value over here. Use interpolation to get this value between 0.2647 and 0.3938. Okay, if you do the interpolations directly here, you have Fx and eta is equal to 0.359. Use interpolation to get this value. Since Fx and eta is equal to u over u capital, then you can find what's your velocity on this one. You have 0.00718 meter per second. So at that point, you have this capital U equal to 0.02. Is it meter per second or is it feet per second? And you have over here somewhere where y equal to 10 millimeters. The velocity component is 0. Very small, 0.0718. So that's example of boundary layer. You can calculate any other parameter on this flow. For example, you can calculate delta, for example. What's the boundary layer thickness? What's the boundary layer displacement thickness? What's the boundary momentum thickness? What's the TW? You're able to calculate all of them using this approach. Okay, any other questions? And once you get TW, you can actually calculate what's the drag, what's the friction drag experienced by this flow. Okay, no questions. You can also ask on the chat features if you would like to, or you can send privately, doesn't matter. Okay, no questions?
No, sir.
Good, yeah, I think
Everything's clear.
you're able to grasp the concept on this. The second approach to do this is using what we call the momentum integral equations. So this one is used to obtain approximate information on boundary layer growth, and then it can be applied to laminar or turbulent boundary layer with or without a pressure gradient. So it provides more comprehensive compared to the Blasius solution on this one. We'll have an example comparing both of the approach to solve this, both of the solutions. Okay, so again, if you take a look on the boundary layer growth or developments across the flat plate over here, you're going to have increasing boundary layer thickness across the flow, where delta x over here. And you have TW as a function of x also, because it's going to change across along the flow, direction of the flow. So if we assume pressure constant throughout the flow field and the x component of the momentum equations within this control column, so you will have F this integration of m dot v rho v dA, and if we consider the x directions only, so you have this, and then for a flat plate with known width of b and from b, so the drag force is equal to the integration of TW dA, or you can take out the b value, so it's going to only depends on the y. TW dy will be your drag force, that the fluid exert on the object. So this is your drag force, and then since the plate is solid and the upper surface of the control column is streamlined, there is no flow through this area by the wall. So the drag force, there is no flow on the n direction, on the vertical directions, only on the x directions. So the drag force can also be derived from these equations. And then according to the conservation of mass, we have this equation on this. So this, bear with me first. So the drag is equal to this is the momentum change, momentum integration of the momentum on this, and they will balance the shear drag. So there is a balance between the shear drag previously from the TW dA integrations and the momentum integrals on this one. So that is the basis of the solutions when you assume that the momentum is overcome by the drag shear stress. That's the underlying equations. The thickening of the bonding layer is necessary to overcome the drag of the viscous stress on the plate. So the momentum integral equation is solved by von Karman. You try to solve the drag as the momentum integral over here, and then you also introduce previously on the definition of the momentum boundary layer thickness, boundary layer momentum thickness. And then what you do is you try to present the drag force as a function of this momentum thickness, boundary layer momentum thickness. And this applies for laminar or turbulence. This one. And then if we try to derive that drag on each of the elemental length dx, you will end up into this equation of Tw as a function of d theta dx, the momentum boundary layer thickness on this one. Okay, but we don't know what's the velocity profile related to this one. What the momentum integral solution try to provide is, if you assume several velocity profile, and then work from there. For example, if your velocity profile, if you have u equal to for linear one, for example, u equal to x times u, for example, or u equal to u times sinus x, for example. So there are several velocity profile that can be used. I mean, you try to use the momentum integral equation to solve for each of the profile. So if we introduce if you already have this Tw equal to rho u squared d theta dx, then try to solve for the boundary layer thickness or other parameter, you can have this what do you call this, the solution for the Tw, where C1 and C2 depends on the flow properties or flow characteristics and the fluid properties also. And we can also actually try to implement this using the Blasius solutions. I mean, Blasius, so the way to see it is Blasius solution is a simplified momentum integral equation also. It means like Blasius solutions, you can derive the Blasius solutions from the momentum integral equations. If you assume that first is laminar, if you use the same assumption on the Blasius and then implement that into the momentum integral equations, you will end up with the same result. So, and it is shown on this part over here. Okay. So the momentum integral equation depends really on the velocity profile that you choose to be included in the solutions. So this gives you several velocity profile, several velocity profile in the boundary layers, and then corresponding boundary layer thickness and so on. So the way you see this, you have a Blasius solutions where the delta is equal to 5, as we previously obtained. You can also have a linear velocity profile. U over capital U is equal to y over delta. It means like you have, as the x increase, the y will, the delta will be like this. And you can also have parabolic one or cubic one or sinus wave one. Which one is the right one is actually depends on the velocity profile actually occur for your flow. So all of them are correct. It means like, because some of the flow will follow different velocity profile. The momentum integral equation is try to approximate the result when you have the velocity profile of the actual case. So you have to choose which one that close to your velocity profile to be able to compare them. And okay, so this is the momentum integral equations, and then for a flat plate with a given length L and width B, and the net friction drag dF, and also the frictional drag coefficient CDF, we can derive those equations to get these solutions. And it is confirmed with the Blasius solutions. We have this one over here. So we can have because ultimately we want to know what's the drag force, actually, the friction drag force. That's what we are looking for by first calculating what's the delta, what's the and also what's the CDF. So we can have that also. Okay, we'll go to example to have a better, to try to grasp this concept of momentum integral equations. Okay, and then we'll try to compare with the Blasius solutions for specifically for the laminar flow in the flat plate. So this is an examples of the use of momentum integral boundary layer equation to solve for the in this case shear stress. Okay, so we have a laminar flow of an incompressible fluid plus a flat plate of, yeah, and the boundary layer velocity profile is okay. Now over here you are given the velocity profile. In our case, it is a linear one because here you have u equal to u times y over delta, or u over capital U is equal to y over delta. So this is a linear velocity profile. It means like the velocity is increasing linearly as the y increase into the boundary layer thickness. So this will be your velocity profile compared to, for example, if you have another one is parabolic or any other velocity profile. So this one is linear. Is it reasonable approach? They may have this for very viscous, for example. You may have this velocity profile. So let's say you have that velocity profile. If you have this kind of velocity profile or linear velocity profile, what will be your shear stress? Okay, so that's the questions over here. So the shear stress based on the momentum integral boundary layer equation is defined as rho u square d theta over dx, where theta is the momentum thickness of the boundary layer. And for the laminar flow, we know also Tw equal to mu du dy at y equal to 0. So we have at y equal to 0. We have this tau w is equal to mu u over delta over here. And then from the equation of the momentum boundary layer thickness, this is the definition of the momentum boundary layer thickness. Then we try to integrate over from 0 to infinite, and then of dy, okay. And then we can for our case to get until delta only on this one. So this is your chance of the limit, because you only apply for the for the boundary layer thickness. So if you substitute them, integrate, you will have this boundary layer momentum thickness of delta over 6 in relation to the boundary layer thickness. We don't know what the delta is. We only know that it's linear between the velocity profile and the momentum, sorry, and the boundary layer thickness. But we can combine this, the norm of TW or this and this, yeah, to get this solution. Mu times free stream velocity divided by delta is equal to rho u square over 6 d delta dx. So you actually substitute this into 3 into 1 d theta dx, yeah, and also to here. Okay, so this TW is mu u over s, and this one coming from this equation. So this part coming from equation 1, this part coming from equation 2. Equalize them to get the relations, to get another relationship of delta in terms of x. And then, so we have this simplification from this. And then
Integrate both, yeah.
yes, exactly. The integration is from x equal to 0, okay, and then to any x, So you integrate from 0 to x. Up here. So you have this, and then you can conclude from delta is equal to, we can input all the known parameters. On this case, square root of this, yeah, square root of 12, and then you have p as the mu over delta, and then so you have this 3.46 px over u. That will be your delta over here. Okay, so we have this one, and this shear stress at the wall can be obtained also from here. You can just input this into this. So you substitute this into equation 2, or yeah, 1, 3, or 4. So you can have this solution on this one. So from here, using the momentum integral boundary layer concept, you're able to derive the you have to go to calculate the boundary layer thickness and also to calculate the shear stress at the wall, but only if you given the velocity profile. So in our case, the velocity profile is linear, so we have this. Okay, but we can, over here you are required to find using the Blasius solutions. We can also do that, and then I think I will try to bring the Blasius solution for this case. Okay, so we can try to calculate using the Blasius solutions for this problem, where the Blasius solutions is given by this. So we can compare this one, I think, here. So we can compare between this and this. This is the Blasius solutions, and this is the solution, the momentum integral solution when you have linear velocity profiles. Sorry, it should be with this one. Sorry. This one and this one. So you only have a different coefficient on this. 0.289 over here, you have 0.332 using the Blasio solution. So these examples give you a way to find the shear stress or actually any other flow parameters, friction, drag, and so on, by using the momentum integral boundary layer equations. If the velocity profile is given or known, or you can actually assume what's the relation between this one is the velocity profile over here. That will determine this, because when you try to find the momentum thickness, u over u is given. So this case is replaced by this. Sorry, replaced by this one, because the u over u is given this. How about if you have a different relation, then u over u capital will be different. And if we compare, then we have this. And this actually give you the comparison between the momentum integral boundary layer concept with the Blasio solutions. And if you compare with different velocity profile, Blasio is one of them. So this is Blasio solutions. This is when you have a linear. I think what we did was linear. This one over here, or parabolic, or cubical, or sine wave. So yeah, I think laminar is way different, but of course it depends on what kind of flow you have. You might have that velocity profile also. Okay, any question until this point?
No, sir.
Yeah.
No, sir.
No, sir.
The takeout from here is if you're given a boundary layer problem, you can solve it using the Blasio solution if it is laminar on a flat plate. Okay, but if it is on different case, then you can use the momentum integral equation to solve it. But the momentum integral equation require you to have the velocity profile. So although the momentum integral equation give you more flexibility on applying the solution to all the laminar and turbulent or the profile geometry, but it's not actually complete solution, because now you have the questions of what is the velocity profile of it. So that's the limitations. The Blasius is simple, a direct solution, but it's really limited of the laminar boundary layer and a flat plate. The momentum integral is more coverage it has, but you should assume, or you should have the velocity profile in order to use it to find the solution of the boundary layer on this one. So both of them has limitation on this. So that's a takeout. Okay. Okay. Now that's about the boundary layer. I think I can continue a little bit on transition from laminar to turbulent. So the flow can change from the laminar to turbulent because as the Reynolds number is a function of x, u times x over viscosity. So as x increase along the flow directions, then you have an increase of Reynolds number, then you're going to have a turbulence, and then so you're going to have a laminar, transition, and turbulent in one flow. Okay, so that's why you have transition from laminar to turbulent, as we can see in, for example, in this figure like this. Where is it? That's the transition process, something like this. Yeah. So you go from laminar, turbulent, and so on. Even on the flat plate. So even if you have a flat plate, beginning with the laminar one, you eventually will get into turbulent as long as you have enough length to happen. Okay, even like you start at very low Reynolds number, for example, because the velocity is small and because of the viscosity is so high, you start with the laminar flow, but eventually when you have a bigger x, you're going to have turbulent one in the one flow, just because of the increase of the x from the distance from the leading edge. So the transition is so the convention is you have this critical Reynolds number 5 times 10 to the power of 5, although it's actually a range, but the convention is as long as you have this single value, then you will have this transition from below this you have laminar, above this you have turbulent. Why do we care about that? Because you have a different equation for the flow characteristic between the laminar and turbulent. If you're already on the turbulent one, you cannot use the Blasio solutions. That's example how important to determine whether it's laminar or turbulent. Okay, yeah. So the transition began with a random location on the plate in the vicinity of Rx Reynolds number. Sometimes it's occur because there's some small disturbance, which crowd decay, and then if the disturbance occur at the location with less than critical, then it will die out. I mean, the disturbance will die out. But if it is already in the turbulent regions, then it will grow and become more and more turbulent. So as I mentioned, so it's concluded we have the boundary line on a flat plate will become turbulent no matter what, as the plate is long enough. So this is something that will occur. So for the, so you're going to have different, so this is an example when you want to calculate where's the locations of the transitions. I think this is pretty straightforward example. You just need to calculate the Reynolds number on this one. A fluid flows steady past a flat plate with a velocity of this. And then if the fluid is water, or if the fluid is glycerin, or if the fluid is standard air, so that will have a different viscosity. So if we the boundary layer things according to Blasio solutions, the boundary layers remain laminar up to this point. So this is actually from the definition of Rax critical, where it's equal to 5 times 10 to the power of 5. So yeah, so we have X critical obtained from this one is equal to 5 times 10 to the power of 5 divided by velocity is 10 times the viscosity, which we have 3 different fluids, so we have 3 different viscosity. So the corresponding delta or the boundary layer thickness is delta at x equal to x critical. So we just need to replace, or what do you call it, substitute the x value on this, which is 5 times 10 to the power of p, into and feed it into this x over here. So you will have x critical and delta critical. It's actually x will represent how much, how long or how far from the leading edge. So this is x, while delta critical will have how height you from the wall when that occurs. So this is x critical, so this is delta critical. So how long from the leading edge and how high from the plate of that when the transition occurs. Then we have this. So if we try to analyze what we have over here, you will see that a big variations of the x critical. It means like for water, you're going to have a really short distance of laminar flow of 0.6 feet, less than 10 centimeters, I think. Yeah. No, 0.1. About 18 centimeters. You're going to have a turbulent case. When you have air, on the other hand, you go even further away because it's less viscous. Means like you're going to have the transition at 7.85. For the glycerins, you're going to have 640 feet, far away from the leading edge to have this turbulence occur. So this gives you an idea how the viscosity is going to affect that flow characteristic. Okay. Any questions this point?
No, sir.
Okay, good. So I think let's see if we have some. Okay, this is transitions. This is the visualization of what's going on during the transitions. And then this is boundary layer velocity profile change as goes from laminar to turbulent. So the turbulent profiles are flatter. The turbulent is this one over here. So it's like kind of like nothing happens, and then you suddenly have turbulent velocity profile. While the laminar one is you have a linear increase until a point, then you have this profile of the u over u velocity profile. Okay. And with that, actually, there are empirical equations available for different flow condition over a flat plate. The CDF, as a function of Reynolds number, L is the length from the leading edge. Why don't we use X? It's actually the same. X determine a particular or any X value, but this one L is when you have a laminar flow, when you have the critical transitions and you have a turbulent flow, and this is when you have a completely turbulent. How come this happened? Well, you can see like this one, you can consider is as completely turbulent because it's really small part of the laminar, then you suddenly have turbulence. So for water, for example, in our case, we can assume that it's all turbulent. While over here you have a considerable length of laminar before it's going to turbulent. So empirically, instead of have to do this all calculations, and then for CDF you can use these empirical equations obtained from experiments for any of the flow characteristic, flow over a flat plane. Okay, one more. So if I use these empirical equations, how we calculate the drag, for example. So this example give you an exercise on using this one instead of having those momentum integral boundary layer calculations to solve this. But this is kind of like a shortcut to do it. But you already have the fundamental concept on how to get into this. But this one is from the empirical. Let's try to use that on a practical problem over here. You have the water ski. So this is waters, and then you have ski over here, and then given width, given the length also, I think, yeah. You have the fluid properties, and you need to calculate the drag caused by the shear stress on the bottom of the ski for various velocity. So you're going to implement any of these equations for laminar, for transitional, for turbulent, for example. Okay, so the friction drag dF is equal to it's called characteristic pressure, half of rho u square times the area. So this is the area times the drag coefficients. A is given, L times B is 2 feet square, the density of the water, the viscosity of the waters. So we can find dF as a function of CDF because we're going to use different CDF according to the flow, whether it's laminar or turbulent. Okay, so once we have that, we need to determine whether the flow is laminar, where's the critical ones, where's the turbulent one over here. So the velocity is from 0 to 30 feet, right? That's what the problem said. So you have to include each of the, let's assume that velocity is, for example, 30 feet per second. What will be your, if you use 30 feet per second, for example, so you have these equations, okay? If you use 0, then you have this part, laminar flow. If you have 10, for example, then if u equal to 10, then you already have on your turbulent. If you use below 10, for example, 5, you have on this transitional. So you're going to have a different one, okay? So let's take one, u equal to what is this, 10, for example. So you use this equation, and then at that point, you will have this. So drag force, you just substitute with the CDF into this. Is equal. Then you will have this curve. I'm sorry. This curve accordingly for different value of velocity. And this is this. This is the distance, and this is the drag force. So you can implement, for example, but you will have a different value, different CDF to calculate this and maybe this, okay, depending on which flow you have. So this gives you a shortcut by implementing empirical equation to find the drag force of a flat plate. We're going to have a different one for the cylinder and for the spare, but I think this is a good time to stop. So the recap for this one, the takeout is you have learned to use the empirical equation to solve for the drag force, because this is one is of practical interest when you have a flow and want to calculate how much power you need to propel the motions throughout this friction to overcome these drag frictions. Any questions? No?
Pak,
Yes.
boleh nanya Pak?
Yeah, go ahead.
Kalau misalnya nanti itu pas UAS materi yang masuk tuh apa aja ya Pak, selain yang internal flow dan external flow?
I think we have chapter 8, 9, and then there's also a little bit on the measurements, flow measurements. I think that's what's over there. Let's see. There's going to be open channel flow later on when you have a free surface. So this one is you have now is flow over immersed body, and then you're going to have an open channel flow when you have a free surface. It means like, for example, flow of open conduit, you know, the one that a flow over a channel that has open to air on top of it. So it's called the open channel flow. It's like a river, or it's like apa namanya, selokan ya, selokan juga open channel. That's one of the topic that's also included. So you have pipe flow, you have concept of laminar flow and turbulent flow, you have flow over immersed body, you have a open channel flow, and the measurements, how to experimentally measure the fluid flow parameters of this one. I hope that answers your questions.
Oke, Pak.
Yeah, there's actually an introduction of compressible flow, but I think we agree that, I mean, the lecturer agreed that should not be included on the basic fluid mechanics, but it will be discussed on the aerodynamics and on the election course. Okay, regarding this material, any questions?
No, sir.
Yeah, good.
No, sir.
I think what we have a homework 3. I already post on Immersed, and then this discuss the material until this point. The boundary layer concept, the lift and the drag experience over flow over immersed bodies on this one. I think until this flat plate, we do have a cylinder and spare, but I think we can you get the main concept of boundary layer on this flat plate flow. The cylinder and the spare will have also empirical, but the concept are the same. You have the boundary layer occur on the nearby the wall. Okay, if there is no other questions, I think we can end for today's
Yes, sir.
session.
Sir, for the homework, will it be due on Wednesday or Thursday?
Let's take a look on this one.
Because
How
you
about
posted
homework 2? Yeah, homework 2 already. Yeah.
Huh?
Go ahead. What do you want to say?
Because the one you posted in Immersed is Thursday, 29th of April.
Thursday. Yeah.
So it will be
Yeah,
Wednesday.
you're right. It should be Wednesday. April 29 is Wednesday, right?
Yeah.
Okay. Yeah, I think I mistyped that. So the point is actually I want you finish before the class on Thursday. So if you have any questions or you want to, I will post also the solution of that by our next Thursday meeting.
Okay, sir.
So how do I change this? So it should be Wednesday, April 29. Okay, Jan. Any other questions?
No, sir.
Good. I think you had the homework to submit it also last night, right?
Yeah.
I think I'll give the solutions through this group after this. So another question. Thank you very much, and then I'll see you next Tuesday, right?
Okay,
Thank
sir.
you. Have a good evening. Bye.
Thank you, sir.
Sir.
Makasih, Pak.